Okay. Good evening, Sachin. Can you hear me?
Yes, sir.
Uh, 1 second. One second. Yeah, Sachin, can you hear me?
Yes, sir.
Yeah. Good. Good evening. Uh,
Good evening.
how are you doing, Sachin?
Yeah, it's going good, sir.
You are a UG student, right? Uh, like if I'm not wrong,
No, sir.
UG,
PhD first year.
PhD.
For coursework I'm doing.
Ah,
Yes, yes.
okay, okay, okay. Yeah, yeah. Apart from this, what else courses like are you taking? Like as part of your coursework?
Yeah, CFD I've taken and
Ah, okay,
composites.
okay, okay,
Uh, then one more, this FEM one
okay. You have to do
and
four, right?
vibration. Yeah, four.
Okay, okay, okay. So your work is on?
On composites.
Okay.
Sir, is there any books related to this? Because after reading through the lecture videos, it was bit
Yeah.
difficult to go through the problems which were given in assignments.
Okay, okay. So the thing is, whatever like till this week, whatever is being taught, it's not like uh, kind of it's very mathematical. Like you won't find these things in interpolation, differentiation, differentiation, numerical integration. Like of course you can find the numerical quadrature, like Gauss quadrature in finite element books, but this interpolation functions, all these things are like very mathematical things.
Okay.
So like for these things you just like you just try to solve this. Maybe you can find some uh, NPTEL course on numerical methods where they will teach uh, interpolation. Like there is one course by Professor Niket Kaisare. I think computational methods, something computational methods. You can search. You will get those videos. In that, he has taught interpolation and all these things. But whatever we are learning till now, like you don't need to be very like you don't need to go very deep into these things. Like if you just know, because these things we like FEM take cares of it. FEM take cares of this interpolation integration. Like we'll just use some functions while we code. So it's not that we have to write and solve each time this, like we have to fit a polynomial. We are just learning this so that we have to know what are the different kinds of interpolations that can be done, and like to have a broader view of interpolation. But as you go through, like you won't need it much, but like if you want to learn deeply about these interpolation techniques, you can uh, go to this NPTEL course, or like there are also some books on numerical methods uh, that also you can refer. Like there is one book by Professor SP Venkatesan. So he's also from IIT Madras. Like computational methods, related to that only. Like there is a book. Uh, if you like. If you want those books, like you can mail me, I'll send them. Like if I think I have the PDFs. uh, if you want, like you can contact me, I'll mail them, so you
Sure,
can
sir.
refer to
I'll
these books.
send a
But
mail.
yeah, yeah, So it's like finite element method for finite element method. There is a book by Professor Manish Srikhande itself. Like he has a book uh, on finite element method. Uh, that is a very good book. Like you can refer to that. And another book if you want, another like some other book to uh, read about finite element method, you can also refer to this book by Asghar Vatti, Fundamentals of Finite Element Method. That is also a very good book. Uh, you can refer to that book. Like it will be very simple. Like if someone like or like if you know continuum mechanics well, if you are like good in this using these indicial notations, like very mathematical kind of teaching or learning a finite element method, if you want to do, like you can also refer to a book by uh, Professor Jain Reddy. So that is also a very good book, but that will be like very mathematically intensive. But these books by Professor Manish Srikhande and also by Asghar Bhatti. So these books are like uh, very friendly to someone who just knows like mechanics, not that much like continuum mechanics or initial notations. Even if you don't know, like you can read this book and learn. So like we'll go through the course then. Like next week, I think. Like this week we have started the introduction. From next week, like we'll be from third week, like we'll be going deep into finite element method. So, but these lectures, whatever uh, professor is teaching, he like these like lectures are very comprehensive, but like you need to be uh, very attentive while listening to these lectures. Yeah, of course, if you want problems, you can refer to these textbooks. Uh, Lot of textbooks are there, but these are some texts which I will suggest. And yeah, okay. So good evening, everyone. So today we are discussing about the week 2 content of this course on finite element method and computational structural dynamics. So as you know, like this course is taught by Professor Manish Vikhande, and I am Syed Shabir Ahmed. So I'm a research scholar in the Department of Applied Mechanics and Biomedical Engineering in IIT Madras. So I'll be taking you uh, through this like a few problems, and like we will also summarize a little bit what was taught during the week, and we will also discuss if you have any doubts related to the content or like while solving the assignment uh, 2 of this course. So first, last week itself, we have started with interpolation. So interpolation is nothing but, let's say if you have some uh, if you have conducted a measurement and like you have data at like discrete points, like let's say this is your like you are conducting some measurement and you are conducting data at some discrete point. Like let's say you are measuring some uh, measuring distance traveled by a car like at different time instance. Let x be the time and like f of x be the distance traveled by the car. So at t is equals to 0, it is 0, and at t is equals to 1, it is 1, and at t is equals to 2, it is 1. Like if I plot it, it might it will look something like this. If I say t is equals to 1 and t is equals to 2, something like this it will look. Or let's say if you have some other measurement, like some other experiment which you are doing, like you will get data in discrete points. Like you will not get a function, right? Like while doing an experiment, you will get a data like this, something like this. Let's say temperature in a city at different times or something like that. So if you want to estimate the temperature at some other time other than the points at which it is measured, so we have to do interpolation. So to do interpolation, what we can do, like I can take just these 2 points. I know these 2 points, like I know the xy coordinates of these 2 points. I can just fit a straight line, and from this straight line, I can use this equation of straight line to estimate what is the value of temperature at this time. That I can do. So, but like always, like if I want to estimate the temperature at different points, let's say like you will be uh, you will have to do this lot of times. Like at somebody is asking you to estimate the temperature, what is temperature at like various times at different points of time. So you cannot go and fit a straight line each time and do the interpolation. So the best thing we can do is like whatever the data which we have collected. So through that we will just pass a curve. So we will just fit a curve. So this curve is something which we will use. Like this is a curve, and this curve will have some function form. So that we have to get the function form of this curve. So like this, let's say this is f cap. This will be nearly equal to the actual function, but this will not be a like accurate thing, but this will be near to the actual function. This we can call it as interpolation function. Interpolation function. So if I have this interpolation function, now I can use this interpolation function. I can substitute different values of x, like at different times. I can estimate temperature at different time instance using this equation, right? So like work becomes much more easier. So that's what we are trying to do here in interpolation. We are trying to find this interpolation polynomial. So we have learned like there are different things we can do. So the best thing we can do, like or the easiest or a efficient thing which can be used to fit a curve is a polynomials. Like we can take a set of polynomials, like any data which you have, you can just fit a polynomial passing through it, and you can just let's say uh, you if you have 3 points, you can fit a cubic not a cubic but a quadratic curve passing through it. So like if you have 4 points, you can fit a cubic curve like that. So we can fit curves passing through these points. So that we can do. And after fitting the fitting the curve means like we have to estimate what are these coefficients for the data which is passing through. So there are like different methods to do polynomial interpolation. One of the method is Lagrange interpolation. So Lagrange interpolation, we have seen that uh, here we have seen like you will take a polynomial like this, like x minus x1, x minus x2, x minus x3 up to x minus xn. So here x1, x2, x3 and xn are at different points at which like we have taken measurement, or at different points at which we know the value of the function. Okay. So at this point this will be this function will vanish. Okay, phi of x will vanish, and it means like we want to like exactly fit the curve at this point. Like so, the curve should pass through these points. Like it should definitely pass through these points. So like what we can do is like we can take this Lagrange interpolation polynomials. So defined as L1 of Li of x, and like for each point we can define a for each node we can define a integrating polynomial like this. So, and after taking this interpolating polynomials, and like we can take the summation of this Lagrange interpolation functions, and we will get the interpolation polynomials. Okay. So it's like explaining it is difficult. We'll see an example. Like we have a problem here. Okay. So I will say like you also try to solve along with me. So uh, so these are the data points. Okay, x is equals to 0. At x is equals to 0, f of x is 0, and at x is equals to 1, f of x is 0, and at x is equals to 2, f of x is 1. Okay. So now I have to find an integrating polynomial, uh, integrating interpolation polynomial to passing through this data. So, like the question here asks us to use the Lagrange interpolation polynomial, like Lagrange interpolation to fit the problem. So there are basically 3 points. So like there are 3 points. X naught, y naught is equals to 0, comma 0, x1 and y1 is equals to 1, comma 0, x2, y2 is equals to 2, comma 1. So these are 3 points. Okay, like if let's say if I have a curve like this and draw 0, comma 0, this is 1 point, and 1, comma 0, this is also 1 point, and 2, comma 1. Uh, what is that point? 2 and so these are the 3 points. I have to find out what is the curve. Okay, let's say this is the curve passing through this point. I have to find out the equation of this f of x, like f cap of x equals to something. I don't know. I have to find out. So first we have to write the Lagrange basis functions. So Lagrange, like we have written, right? So we know that we know that Fn cap of x is equals to I is equals to 1 to, let's say, n plus 1. Here uh, n is 2 because 3 points means like you can fit a quadratic curve to it, passing through it. So here for our problem n is 2. Let's we'll write it like Li of x equals to f of xi. Okay. So now let's find out. Now let's expand this. Let's expand this. N will be 2 because from 2 points we can pass a parabola passing through that, uh, or a quadratic curve passing through the 3 points. Okay, which exactly passes through all the 3 points. So this will be f of n 2 plus 1, or like let's say you can say 3. This will be Li of x f of x. And further I can write this as f2 of x is equals to L1 x uh, f of xi, L2 x. I'm just expanding the summation, f of x2 as L3 x f of x3. Okay, so this will be my interpolation function. Let's uh, let's rename this. Like I will write this as x1 y1, x2 y2, and x3. Okay. So we will write what are the basis functions. So step one is like we will define what are the basis functions. So basis functions are L1, L2, L3. Okay. Basis functions. The basis polynomials. So for this L1 of x, we will write it as x minus. So for the first point, you have to take these 2 points. Okay, we will not take this. So L1 of x is equals to L1 of x is equals to x minus 1 into x minus 2 divided by, or let's write it like this. Okay, first I will write it like x minus x2 x minus x3 divided by x1 minus x2, right? x1 minus x3. So this is the first basis function. So now I will substitute x1, x2, x3. We know what are the values of x1, x2, x3. So this is x1, this is x2, and this is x3. Okay. So now I will substitute that x minus 1, x minus 2 divided by 0 minus 1, and x1 is 0, right? So 0 minus 1 and 0 minus 2. So now we will get x1 minus x2 by minus 1 minus 3, it will be plus 3. Sorry, this is 0 minus 2, 0 minus 2, x1 minus x2. So this will be 2. Okay. Similarly, L2 of x will be, now I will take all the other terms except x2 because this is the second polynomial function, right? So I will take x minus x1 into x minus x3. So I have missed x minus x2. So that is what we have to do. Now the same thing I'll substitute in terms of x. I'll substitute x2. Okay, x2 minus x1 into x2 minus x3. So this will be x minus 0, x minus 2 divided by 1 minus 0, 1 minus. So we will get minus of x into x minus x2. So this will be the final. This will be the final uh, L2 basis function. Similarly, I have to define L3 of x. Now I have to take all other terms except x3, which have x3. Okay, so x minus 1 into x minus x3 divided by, sorry, x minus 1 into x minus x2 divided by x3 minus x1, x3 minus x2. Okay, so this is x minus 0 into x minus 1 divided by 2 minus 0 and 2 minus 1. So we will get x into x minus 1 by 2. So we have the basis function now. We have the basis function. Now I can write the polynomial function. So integration polynomial. So this integration polynomial using Lagrange interpolation will be L1 of x into f of x1 plus L2 of x into f of x2 plus L3 of x into f of x3. So we have calculated all the L1, L2 values. L1, L2, L3 values. F of x1 is already there in the this table, right? So f of x1 is 0, f of x2 is 0, and f of x3 is 1. So I'll substitute all these values like let's say this is x minus 1 into x minus 2 divided by 2 into f of x1. X1 is 0. So I'll substitute I'll just write the value of x1. This is minus x into x minus 2 f of 1 plus x into x minus 1 by 2 f of 2. So we know the values of f of 0, f of 1, and f of 2. We'll just substitute them also. So this will be f of 0 is 0. So whatever I multiply this with 0, that will become 0. So that first term will become 0 automatically. So f of 1 is also 0. So whatever is there here will also become 0. So 0 plus 0 plus this f of 2 is 1. So now I'll substitute the value of f of 2. That will give me this. So my final interpolation polynomial passing through the 3 points will be this. So this is the final Lagrange interpolation of the polynomial interpolation function, which will pass through these points. So this is the polynomial which is passing through these points. So now I can use this function to interpolate any value. Like let's say somebody asks you what is the value of f of x at 0.5 or 1.5. So you can just substitute in this and you can tell that this will be the value of this function or temperature at this time, like that. So you don't need to go to the table, fit a line, and do all these things. So I hope this is clear, right? Any doubts in this? So this is yeah, Sachin. You have anything to ask?
No, sir, no doubts.
Okay, okay, okay. So like you have some tabulated data, which might be experimental data or something. You want to fit a function to it so that you can evaluate this function at different points uh, other than the tabulated data. So like we do, right, like lot of times we use this trigonometric function, trigonometric tables or some other kind of tables in some data books. Maybe in some design books, you will be having these kind of tables that will be in this tabulated form. But uh, if you want the value of the function at some other point, you just fit a straight line and you interpolate it. Instead of that, what we are doing is we are just fitting polynomial to it. And if we know the expression of the polynomial like this, I can just put the value of whatever estimate I want to take, and I can get the value. So this is the Lagrange interpolation uh, polynomial which we can use. So this is one way to do polynomial interpolation. There are also other ways, like we will see. So like this. So we have like the function Lagrange interpolation function will be of this form. So like these are called L1 of x is called as a basis function. So and f of xi are the known values of the function. So these are the known values f of x1, f of x2, f of x3. So we have to first define the basis, and after that uh, we can use this summation to get our polynomial. So now you can see if I substitute f of x f of, in this interpolation polynomial, if I substitute x is equals to 0, if I substitute x is equals to 0, I'll get this as 0, which is equals to our uh, our function, our values which we have got even in the table, right? So f of 0 is also 0. Now, if I substitute uh, x is equals to 1, now I will get 1 minus half. You get, if I get in, there is some, yeah, this is x minus 1, x minus 1, sorry, x into x minus 1 by 2. So now if I substitute x is equals to 1, this will again become 0, which will be equal to the value which is given in the function. Now if I substitute x is equals to 2, I will get uh, 2 into 2 minus 1 by 2, which will be equal to 1. And this will be also equal to the value given in the function. So this function, whatever which we have built, which we have constructed, is exactly passing through the points. So this function will exactly pass through these points. So that is the advantage of using Lagrange interpolation, that this will be passing exactly through these points. But we don't know, like it will be like exact in between the points. At these points, the function will have zero error, and other points it might not be having like exact thing, because yeah, this is it will like approximate. So this is Lagrange interpolation, and this is one kind of uh, example which we can take on like Lagrange interpolation. Like, of course, you increase the number of points, the polynomial degree will also increase. Like, if you have 4 points in this table, if you have 4 points in this table, you have to define uh, 4 basis functions, and each basis function, again, you will get one extra term here, x minus x4 you will get. So degree of increase. So because we have 3 points, get this is a quadratic function, right? So for 3 points, you will get a quadratic function. So this is x square minus x by 2. So this is a quadratic function. Degree of polynomial is 2. So that's why we have written 2 here. Okay. Now let's say uh, instead of just giving the function values at different points, you also have the derivative of the function at those points. Then you can use some kind of interpolation, which is called as Hermite polynomial interpolation. So like all these things like are very mathematically intensive. Like you can derive this, like you can read about this. I don't want to go deeply into that. But the thing is, final thing which you should know is Hermite polynomial interpolation. Let's say you have some let's say you have some data like this. Mm. X, f of x, some table will you will have like x is equals to 0, 1, 2, 3, 4, something like this. But let's say if you also want the derivative of the function to match, exact function to match, then you should also get this from some kind of experiment or something. Let's say you are like uh, you are measuring the body, how much distance it is moving, and also you are measuring its velocity. So f of x is the distance traveled by the body, and f dash of x is the velocity of the body. So you have two uh, values, like one is the position of the body and one is the velocity of the body. So let's say this is f of x and this is x. Okay. And these are some data points. Okay. These are the different position of the body at different times. So the slope of the displacement curve is nothing but velocity, right? So we want to fit some polynomial like this. We want to fit some polynomial like this, passing through these points, such that the velocity or the slope of the curve at these points is also equal to the data which is given or the data or the measured data. So like in Lagrange interpolation, we were just concerned about the curve should pass through these points. We were not concerned about if the slope of the curve is matching. Like we don't know. Like there was no slope of the curve which was given. So we were just making sure that this curve is passing through this data points. In Hermite polynomial interpolation, we will make sure that the function passes through these points, and also the slope of this curve which is passing through these points is also according to the data given. So it will match, the slope will exactly match with the data which is given. Okay. So that is like you are giving one kind of extra constraint or one kind of extra condition which has to be which has to be satisfied by our polynomial interpolation. Okay. So the function has to satisfy. First condition is it has to pass through these points, and the second condition is it also has to uh, satisfy the derivative condition at all those points. So that is Hermite polynomial interpolation. So like we can use this like if you have n number of points, like you can use lot of points and you can do this. Uh, but the easiest way is like a better way of using is better way of doing this Hermite polynomial interpolation is piecewise cubic Hermite polynomial. Like I will explain what is that. So let's say you have like some n points. I don't know like how many, lot of points, data points. From measurement, you are measuring the distance traveled by the body, and also you are also measuring the velocity. So this is the distance plot or the displacement plot, and it is looking like this, something like this. Okay. Now instead of taking all the points at once, like let's say like these are the number of points. So at each point there are two conditions, right? At each point there are two conditions. So one is the curve should pass through this point, and the second is the velocity or the derivative of the curve or should be equal to the uh, data, the value which is given. Okay. So at each point there are two conditions. So if you have if you have like n points, you have two n conditions. Okay. So with two n conditions, you can fit a polynomial of 2n minus 1 degree. Okay. Like we had 3 points in Lagrange interpolation, we had 3 points. So 3 points, and also only there are three conditions. Derivative condition is not there. Three conditions are at 3 points, the curve should pass through these 3 points. There are three conditions are there. So let's say n is equals to 3. So the maximum degree uh, of curve which will pass or the minimum degree curve which will pass exactly through these points is n minus 1. So 3 minus 1 is equals to 2. So we can see, right? So here we got a second degree polynomial. So similar way, if you have 3 points along with the derivative information, in Hermite interpolation, you will get a polynomial of degree 2 into 3 minus 1, which will be equals to 6 minus 1. You will get a degree of polynomial of degree 5. So that is the thing, like as the number of points increases, uh, like the degree of polynomial is also increasing like anything. So earlier we just fit a quadratic curve. Now we are fitting a uh, like a polynomial of degree 5 for just 3 points. So we have already seen last time that as the number of points increases, you can see that this phenomena happens. These polynomials will give a lot of oscillations like this. Polynomial interpolation will give a lot of oscillations like this. So it is not fitting. Like as the degree of polynomial increases, this will be a major problem. So what we can do one thing is like we can take just 2 points. We can just take 2 points. For 2 points, there will be four conditions, right? For 2 points, there will be four conditions. Uh, so we can fit a degree of, we can fit a curve of uh, degree 3 between these 2 points. And then we will take these 2 points and we will fit a curve of degree 3 again here, and then we will fit a curve of degree 3 again here. So what we are doing is we are doing piecewise interpolation. So at each point, uh, like we will divide the curve into different segments, and for each segment we will fit a piecewise cubic Hermite polynomial interpolation function. So, and by using that we can reduce the number of oscillations, okay, because like already the degree is reducing. If the degree of polynomial reduces, the number of polynomials will reduce, and we will get a good approximation to our function rather than taking all the points at once and doing interpolation. Like if we just take piecewise interpolations, like first you have to maintain this uh, displacement like function. Like these two functions will have the same differentiation, and also the value of function at this point should remain same. So that is called p chip. So piecewise cubic Hermite interpolating polynomial. So like you can just use like in MATLAB, or like if you are using Python or like or any other programming language, there will be a predefined function. Like we don't need to do anything. Like we don't need to define, like write anything. That will automatically take care. Like if you just give this data x, f of x, and f dash of x, it will automatically fit a piecewise interpolating polynomial function. So that is one way. Like I'll just show example. So now you can see here. Uh, I am like uh, I have 5 data points. Like let's say this is the temperature in a city at like 2 hour interval at zero, at time t is equals to 0, or like 12 a.m. the temperature is 16, then it increases like that. Okay. So if I am fitting a degree 5 polynomial, so like because I have 5 points, right? So because I have 5 points, I will just use Lagrange interpolation and I will fit a fifth degree polynomial, and you can see like this is like very zigzag. Okay. But like you will not expect temperature to fall suddenly here from 16 to 14 and then 14 to 18 in the span of 2 hours. It's not like rational. So, but instead of that, if I use P chip, you can see that temperature is just increasing from 16 to 18. So in this interval, it will have a uh, monotonous property. Like between 16 to 18, it is just increasing. Okay. Like similarly, you can see here, uh, 18 to 20, it is increasing, and then 20 to 18, 20 to 16, like it is again decreasing like this. And you can see here again from 8 to 10, you can see that the cubic, the degree 5 polynomial is like again very zigzaggy. Like it is increasing and then it is again falling. Like it is not a right trend. Like temperature will not behave like this. It will, like for a short interval of time, it will just either increase or decrease. So here using, in this case, using p-chip will be a good idea. So of course we have to get also the derivatives of these points, like at uh, like or the variation of temperature at these points with respect to the time. Like that is another condition also we have to satisfy. Okay. So that is the advantage of p-chip. Or let's say uh, okay, so cubic Hermite polynomial interpolation, we will see one example. Okay. So let's say you have some function, like you have two data points, okay, like x naught and x2. Like you have conducted some measurement. From that measurement, you have two data points, and you want to fit a curve. At these points, you know the value of the, let's say, uh, displacement of the vehicle and also velocity of the vehicles at this point. Okay. Let's say x is some time or something like that. So this is a cubic in Hermite polynomial. Like this, we can like expand this for n is equals to 2, and if we do this, like we will get this function. Like no need to like go through. Like if you want to derive, like you can take pen and paper and like do the calculations and get it done. But no need to do. Like there is all, like standard formula is there. Like if you have 2 points and at those 2 points you have the function values and also you have the derivative of the function at those 2 points, you can use this cubic Hermite polynomial and get a polynomial function. Okay. So let's like here there are different terms. So h00t, and t is something which we define as x minus x naught by x1 minus x naught. So and these are like different functions which are there. So we will understand this with an example, and we will solve this. Okay. Okay. So this is my x naught and this is my x1. Okay, here this is my x naught and this is my x1. This is f of x naught and this is f of x1, and this is f dash of x naught and this is f dash of x1. Now I want to find out the cubic Hermite integration interpolating polynomial passing through these 2 points. So and then after finding out the interpolating polynomial, I want to find out what is the value of the function at f of pi by 2. Okay, let's do it. So first, we can just define t here. T is equal to uh, wait a second. Okay, So we will just like from this we will write what is t? T is equals to x minus x naught. X naught is 0 here, or let's say I'll just write first x minus x naught divided by x1 minus x naught. So uh, you just remember this problem. Like this is a similar kind of problem which is given in assignment. You can use this problem, like the method which we have used in this problem, to solve the problem which is given in the assignment. So the ball drop problem is there, right? Like there is a table of values which is given. From that, you want to find out uh, at which point the ball is hitting the ground. So for that, we can use this the same method which we are doing here. I'll explain how. First, we will solve this, then we will look at that. So we will solve this, and I'll tell you how to solve that. I won't solve that problem, but like similar method you can use and solve that problem. So t is equals to x minus x naught is 0, and again x naught x1 is 5 and x naught is 0. So t is equals to x by 5. So this is our t. We know t, what is t, and now we have this. We have to find out this interpolate or this basis functions h0 of t. It will be equal to 2t cube minus 3t square minus 1. Okay. Like standard thing, like uh, it's already there. Like we don't need to do anything. This is like same for every problem. We have to substitute this t value here. Okay. 0, 1 of t is equals to minus 2t cube plus 3t square, and h11 of t is equal to t cube minus t square. Okay. Let's start a paper. So we know that h of x, or the cubic Hermite interpolating polynomial between 2 points, can be given as f of x naught into h 0 h to t plus f dash of x naught into x minus x naught into h1 naught into t plus f of x1 into h01 into t plus f dash of x1 into x minus x1 minus x naught into h11 of t. Okay. We know all these values, right? F of x naught, f dash of x naught, because this is already given in the table. F of x1 and f dash of x1. We will substitute those values. So we will get 1 into f of x naught is 1 because it is 1 given here. H naught naught x is v. Yes. This is uh, x1 minus x naught is 5, 5 comma 0, 5 minus 0, and it is 5. And sorry, f dash of x naught is also given, which is 0. And h1 of 0. Okay. 0 into 5 into 3. And we have f of x1. F of x1, the value of f of x1 is minus 1 because it is there. F of x1 is minus 1 into h1 of h01 of t plus f dash of x1 again is 0. 0 plus 5 into h11. So this and this will become 0, and we will just have h not t minus h01 of t. So this is our interpolating function. Now we will substitute. So if we substitute this, we have 2t cube minus 3t square plus 1 minus of 2t cube plus 3t square. This will be equal to, like, if you do all the simplifications, you will get this as 4t cube minus 6t square plus 1. So now we can substitute what t is equals to x by 5. So substituting t is equals to x by 5, t is equals to x by 5. You can get uh, h of x is equals to 4x by pi cube minus 6x by pi cube square plus 1. Now the final thing which was asked in question is we have to evaluate the value of function at x is equals to pi by 2. So we will just substitute x is equals to pi by 2. We will get 4 into 1 by 2 cube minus 6 into 1 by 2 square plus 1. So if you take this, like, you will get 1 by 2, I think x equals to pi by 2. Yeah, x equals to pi by 2. Yeah. Use, if we substitute, we will get 4 by 8 minus 6 by 4 plus 1. We will get 1 by 2, 3 by 2 plus 1. You will get h of pi by 2 will be equal to 0. Okay. So this is the value of h of pi by 2. And this is the function passing through, these points. So what was the, like, if I can just, you can just take this. So at x is equals to 0, f of x was 1. So 0, f of x was 1. And at x is equals to pi, which is like 3.14 something, like this is pi, this is 0. At this point, f of x was minus 10. So this is the value. And like at these 2 points, we are fitting some cubic curve passing through these 2 points. Of course, we also know what is the slope at these 2 points, and the slope is 0. So this curve will not look like this. Yeah, it will probably look like this because the slope is 0. At this point, the tangent to this curve is 0 because it is given. So this is h of x. Okay. So, and you can see at h is equals to 5 by 2, you can see that this is 0. Like we are estimating whatever we are estimating, like you can approximately say, like, because I am not drawing exactly the curve, but it will look like this. So that is how we can do, like, if you have 2 points, you can use cubic Hermite polynomial uh, and fit a cubic curve passing through these 2 points, provided you should have the data of the function at those 2 points and also the derivative of the function at those 2 points. So that is the condition. Any doubts in this? Okay. Uh, did you guys get to solve the problem? Uh, have you looked at this question 3 and question 4 in assignment 2? Were you able to solve it, or it's like no idea, like you have not solved it, or you will say that no, we have used ChatGPT to solve. So there can be three answers. Manoj,
No, sir, not in solid.
not solved. Okay.
Not solved.
Okay. So I will just give you an idea. Okay. So the question is, a ball is there. Uh, there is a building, some kind of building is there, and you are dropping a ball from that building, like you are just leaving it, like without any force, you are just dropping it. Height of the building is some, let's say, h naught. So you are leaving the ball from this height, and after the after some time, like the ball will go down, go down, go down, and it will hit the ground. So like we don't know when the ball like uh, will hit the ground if we are like solving this uh, using some kind of solver. Let's say uh, let's write the equation of motion uh, of this ball, like equation of motion of this ball for uh, like falling from the building. Like we know, right, uh, s is equals to ut plus half at square, like something, right? Like this is a basic formula. Like you might remember, uh, like using this, I can get what is the displacement at the of the ball at different points of time. Okay. But in general, like uh, if a body is like, let's say, uh, uh, traveling, like traveling or moving uh, or falling, uh, its position is changing. So we can define like equation of motion. Like if I differentiate two times like this, let's say d square s by dt square. So you will get something like this. So the acceleration of the ball will be equal to, like at any point, like, or let's say you are just using Newton's second law. Okay. So Newton's second law, what does it state? F is equals to m into a, and a is equals to something, let's say, f by m. And a is nothing but d square s by dt square. And we know that for a ball falling, for a ball falling from a building, it will have only gravitational acceleration. So that's why we can write this as d square s by dt square is equals to minus g. So this is the equation of the motion of the ball. Like if you integrate it, you will get this equation. Like if you integrate it two times, you will get this equation. But let's say you just have this equation and you are using some solver in MATLAB or Python, like you are coding it and you are solving this differential equation. Like whenever we numerical solve differential equation, we will solve at different time instants. Like at t is equals to 0, at t is equals to 1, at t is equals to 2. Like we will not get a curve like this when you are like numerically solving it. So if you have this function, like if you have this function like analytical solution to the problem, you can just say like you can just set this is h1 minus h naught, you can say, or like because this ball is traveling downwards, so you will get some kind of negative value of yes. So that will be like we have to take care, like height of the building we have to take out. So you can just write it as h1 is equal to h naught minus something like this, you can write. So if I have this kind of equation, I can just put I can just put uh, h1 is equals to 0, and if I solve this, if I if I put h1 is equals to 0, and if I know, like if I can solve for t, I will know at what time height or the distance traveled by the ball is 0, and at that point I can say that the ball is hitting the ground. But most of the times when we solve some kind of problems, we won't have this exact solution to the problem. Like this kind of solution won't be there. So we have to numerically solve it, and we can solve it numerically only at some points. So that's what they have given, like in the next question, like in the question 4, they have given some uh, data table like this. Data table. So like t and also height of the ball they have given. Like 0, at 0 it is 50, and at this it will be 45.095, something like this. Yeah. So at distinct points, like the solver is uh, solving and giving you the value of the uh, location of the work. And at some point, you can see that, and at some point you can see that between I think 3 to 4 seconds, 3 to 4 seconds, you can see that the height is 5.855, and then it is becoming minus 2.480. So this is the point. This is the point. Like in between 3 and 4 seconds, at some point height is becoming 0, and uh, that is the point at which the ball is hitting the ground. So we have to find out what is the time at which this h will become 0. So that is the question they have given. That is the fourth question. So what you can do is, so because like this is a motion problem. For motion problem, like whenever you are doing interpolation, you have to take distance and also the velocity of the function. So velocity of the body, like you calculate velocity, you can calculate velocity also, like using this same table data points. Like you can use the finite difference or central difference formula, and you can get the velocity, like different approximate velocity you can get. So like, so now you will have two conditions. So in between 3 and 4, in between 3 and 4, in between 3 and 4, you can, so t is equals to, this is 3, like just take t and f of t, or like this will be equal to h and f dash of t, or you can say this is velocity. So 3, 4, you will have some 5.855 and minus 2.480. And this we can calculate. So you can calculate approximately what is the velocity at 3 by using this central difference formula, which is f dash. Uh, I will just check it. Central difference. Give me a second. So you uh, can take this central difference formula and you can approximate the value of the velocity at these 2 points from the table's data. You can take this of 5 minus f of 3. So h is nothing but uh, not h. You can write it as delta t. Uh, delta t. So from this by using this we can get our velocity values, and you have 2 points, and for 2 points you have the velocities and also the displacements. Now you can fit a cubic Hermite integrating polynomial. So you will get some curve, you will get something, right? So whatever the thing which we have done here, the same procedure you have to follow, and you will get some curve. H of x you will get. So now some polynomial we will get after fitting it. So this polynomial is nothing but it is showing f of t, right? So this polynomial is like approximating f of t or displacement of the ball. So if I solve this polynomial for like whatever the polynomial which you get, you solve this polynomial for like 0. Like if you put h of x is equals to 0, because we want to find out the time at which height is becoming 0. So f of t will be 0. Then whatever the solution you are getting, like you will get some cubic polynomial, like t cube a something you will get equal to 0 you will get. So equal to 0 is the condition. Now you can take your calculator, substitute all the values which you are getting, like, and you can solve, you can get the uh, time at which you will get the ball is hitting the ground. So you can get the point at which the ball is hitting the ground, which will be I think around 3.19 something. This is the answer for that. So that is how you will solve it. Okay. So this we are using qubit like we are using 2 points here. Like we know in between 3 and 4 seconds the ball is hitting the ground because from here uh, the height is becoming negative. So it is positive here and it is negative here. In between these 2 points, there will be some height at like h is equals to zero. H will become zero. At that point, the ball will hit the ground. So I want to interpolate what point that will hit the ground. So if I if I put this whatever the polynomial I get equal to zero and solve it, I will get the value of t. So that's how we will solve this problem. So so in the third question, they have given like if you want to identify the time of collision, what kind of interpolation you will use? Linear interpolation, linear. Like Lagrange interpolation, linear. So you will just take 2 points and value of the displacement are 2 points. You can get an interpolating polynomial, but that will not be accurate, right? Like because for a body in motion, like if I have also the velocity, then that will give me a good interpolation. Along with the displacement and velocity, if I have both the things, that will give me the exact point at which uh, I want to estimate uh, the body's position. Like if you have both the displacement and velocity, that will be good. So displacement is nothing but the value of the function, and velocity is nothing but the derivative of. So first two options are Lagrange interpolation. Like Lagrange interpolation is not good for this. Then there is cubic spline interpolation. In cubic spline interpolation, along with like in cubic spline interpolation, if you see here, along with the derivative, the second derivative will also be used. Like in cubic spline interpolation, like here we used x. For Hermite cubic interpolation, we used x f of x and f dash of x, right? In cubic interpolation, we should also have f double dash of x also. So that is like three conditions will be there at each point. But that is not required because this is a motion problem. For motion problem, if you have velocity and displacement, it is enough to define the state. So cubic spline interpolation is not necessary. We can take cubic Hermitian interpolation to get the value of time at which the ball will hit the ground. So for third question, the answer is like cubic Hermitian interpolation. Okay. This comes from the nature of the problem which you are solving because this is a motion problem which is in the like displacement, like the equation of motion has a second derivative of time. Then you should have displacement and velocity to estimate the state. Like we will learn this like as we go on this, as we go deep into the course, we will know more about it and you will get more intuition about this. But for now, you just remember that for a motion problem, you should have displacement and also the velocity. Then interpolation will be good. Okay. Anything more than that and anything less than that is like not necessary. Uh, it will not give you an exact idea. Is this clear? Like now, how you are going to solve this problem? You got an idea, or
Yes,
you, like it? Sachin, you were saying something.
yes, sir.
Or
Got it,
someone
sir.
got it right? Yeah. So you have to approximate the value of velocity. Like you can use the central difference scheme. I hope you all know central difference scheme, forward difference scheme, all those things. So
Yes, sir.
you can do it. Yeah. Okay. So now I am just like I have just drawn plotted this curve. So like you can see that there like first I have used a fifth degree polynomial and then I have used a cubic spline. So cubic spline is like derivative is also continuous at this point, and also the second derivative is also continuous at this point, like between these two at this segment. So you can see that cubic spline is like a very smooth, a very aesthetic curve that we can fit the points. Okay, but that is not required always. But that is the most aesthetic curve. Like in CAD, like if you're using um, uh, like SolidWorks or something, like if you are defining some curves or something else, like they will use these kind of splines, B spline, cubic spline. So to define curvatures, like if you have some kind of a cylinder or something like this, they like internally the software use this splines and it will fit the shape of the curve which you are defining it. So that's why it looks more aesthetic to eyes. Like if you have a cylinder, like you can, like in computer everything is discrete. Like you will define some points. Like if you are like using straight line to fit this, it will look like this. Okay, not very good, right? Like, but if you use a spline, it will like almost match the shape of the cylinder. Okay. Cubic spline or some other kind of spline. We have already solved the problem, right? Last time, I think f of x is equals to 1 by 1 plus 2x or something. This was the uh, Range function. And like we sampled the data at like we sampled the value of the function at different points. Like we took x and f of x at different points and we tried to fit a curve. Like if we took like uniform points, you can see that like 10 points I have taken, like at 11 points I have taken, and using 11 points I'm fitting a 10-degree polynomial, and you can see that this is not a very good fit for this curve. There are a lot of oscillations. So then we learned that there are like instead of using uniform nodes like uniform points, if we use some kind of nodes called Chebyshev nodes, like which are again uh, solutions of Chebyshev polynomials, we will get a good approximation compared to the uniform nodes. Okay. Better than that, if I'm using p-chip, like in between two nodes, I am taking an interpolation. Like I am taking 2 points, and at those 2 points, I am taking the value of the function and also derivative of the function to be continuous. And if I'm fitting the curve, you can see that I am getting a very good approximation. Like piecewise cubic Hermitian interpolating polynomial will give me a very good approximation of this Runge. Further, if I use like cubic spline, like you have the data, right? Like you have the data. If you are like making sure that at each point derivative is also continuous and also the second derivative is also continuous, then you will get a very good approximation. Like you cannot like this Range function is exactly fit by this cubic spline. So that's what makes it very good. Like cubic splines are good for interpolating uh, like polynomials like this, uh, and it will exactly fit the curve. Like it will give you a very good aesthetically looking curve, and you can like almost say that this cubic spline is exactly matching the Runge function. So that is the advantage of it. But like of course you don't need cubic spline to be fit everywhere. Like if you have temperature data, like you should use p-chip instead of cubic spline, because like you expect the temperature to either increase or decrease between 2 points. So here you can see cubic spline is also decreasing and then it is increasing, but it is not required here. But when like let's say if you are fitting some kind of shape of a cylinder in CAD or something else, then you can use cubic. So that is interpolation. Okay. Okay, so there are we have learnt lot of different ways of polynomial interpolation, starting from Lagrange interpolation, Newton interpolation, and then we learned Hermite interpolation. Then we also learned cubic splines. Like these things, you just know it, but you don't need to solve any problem in that. But it will be helpful if you are like uh, using some CAD. You should know like what are splines and how they are formed on all this. But no need uh, to go deeper in this course, like where it is not necessary. So then we also went to differentiation via polynomial interpolation. Like you have some data, you have some data like this. I'll just take f x and f of x. Okay, some measurement data you have. Now you want to find out the value of differentiation of this function. So what we will do is like what we have done earlier. We will we can use this like this is the different definition of derivative, right? So limit h tends to 0 f of x plus h minus f of x by h. But as h tends to 0, what happens is these two functions, like when they are very near, and if their values are like very near, catastrophic cancellation happens. Like if you are like let's say giving computer some value as 100.000000001, and if you are subtracting from it, computer will not give you the value exact value 0.0001, but it will give the this value as 0. It will approximate because we know the problem of significant digits. Like computer can only store certain number of digits because there is a storage problem. So that's why like I cannot like decrease this value of h, because as I decrease this value of h, f of x plus h and f of x will become nearly equal. Okay, so that is the problem which we face in computers. So in order to avoid that, we can use something called Richardson extrapolation. So that is something which we can derive using our I hope you all know Taylor series expansion. Uh, yes, Taylor series expansion. So Taylor series, we can approximate any function in using the polynomial. Okay, let's say f of x plus h is there. Then you can approximate it as uh, f of x plus h into f dash of x into sorry plus h by 2 factorial into f double dash of x, something. This is forward difference. You know the values like you should know the value of f of x, f dash of f, f double dash of x. Like you can go on increasing this order h square by 3 factorial, something like this. Similarly, can also have a backward difference. Nothing but minus here, like this. Okay, so this is Taylor series. Now you can see that when you take the forward difference, this is the forward difference formula. The forward difference formula. Using this, we can approximate the value of derivative at x, like, and we will neglect all these terms. We will neglect all this. Okay, that is what we can do using the forward difference formula. Now you can see that this is first order accurate because we are leaving out all the terms, uh, all the terms of all the terms which have higher degree, including one. Then we can also have backward difference. Similarly, like we can also get the derivative of f dash of x using this formula also. Here also same thing we are doing. There is also, like, we can also use the central difference by adding these two. So now you can see that here we are neglecting all the terms after h square. So this is second order accurate. We will see what is second order accurate and all these things. So now you can write this as f dash of x is equals to phi of h. This is phi of h. Okay, this is phi of h plus something something like this. Now you can take, like, you can define the same function for h by 2. You can define the same function for h by 2. Like, you, instead of h, you will substitute it. Like, instead of h, you will substitute h by 2. So using these two equations, using these two equation, I can eliminate the h square term, and now I will remain with all the terms in the degree of 4 and more. So what happens is when h is nearly equal to 0, or like which when h is near to 0, if something is near to 0 and if we square it, like, then it becomes more near to 0, right? So if you have 0.01, if you square it, it will become 0.001. So if my order of accuracy is more, it is a good thing. So this, whatever the terms which we are neglecting should be more than, if it is more, like if it is 4 6, it is good for us, because as h, like, this is the error, right? Like, whatever the terms which we are neglecting is the error. So as h, like, as we decrease h more, this, or like if you take power 4, like, h power 4, it will be more near to this, it will be more near to 0. So that means our error is much more lesser. Okay, so that is what, like, we can, like, in Richardson extrapolation, what we can do is we will get the derivative of the function using central difference at h. Then we will get the same differentiation value at h by 2, and we will use this both uh, differentiations to get another approximation which will be more accurate. So we will see how it will be done. Okay, okay, let's say uh, this is a function, yeah, f of x is equals to e power minus x square. Okay, and I want to find out what is the value of derivative of f dash of x at this point, which is x is equals to 1. Okay, now I can use like uh, now I can use forward difference f of x plus h. Like, you can take any step size, like, uh, we are taking step size from 0.1, and we are, like, decreasing here. You can see we are decreasing the step size further. Like, from right to left, it is going more towards 0, like decreasing the step size. So f of x plus h minus f of x by 2 by 2h. So we can use this, and like for different step sizes, like we can get the uh, we can get the derivative value. We also know the what is the, like this is the analytical function. We also get the actual derivative, which is d by dx of e power minus x square. That will be equal to minus 2x into e power minus x square. So we can get the error, and if I can plot the error for different points, you can see that like as I decrease the step size, the error also will decrease, right? Like it has to decrease. Like uh, if you have a function, like if you want to get the derivative, if you are taking these 2 points and getting the slope of this line, it will give some derivative. But if you take like very close 2 points and like you are drawing a line through this will be a tangent to the curve, and that will give me a more accurate estimation of the derivative, right? So h, if I am decreasing, it should decrease the error, right? The error should decrease like this. But what happens is after this point, error is like if I'm decreasing further, error is increasing. That is because catastrophic cancellation happens in the computer, like round of error will be there. So that's why, like in computer, I cannot uh, go I cannot go take my function, I cannot take a step size lesser than this. Like there is a limit to how much step size I can take. Similarly, if I'm taking the central difference, you can say that error is increasing in a rapid manner compared to the forward difference, because you can see the slope of this line is much more steeper. So you can see at the same step size, central difference has a lesser error compared to the forward difference. So central difference is a better option compared to the forward difference. But you can see again it is also having some problem that after this point error is increasing because there is a some kind of catastrophic cancellation. It is or round off error which is accumulating in the computer. So now if I use the Richardson extrapolation, you can see that this is much more steeper, and order of accuracy is much more even like order of accuracy is even increased. You can see at 10 to the power of minus 3 step size, Richardson extrapolation has a lesser error compared to the central difference as well as the forward difference. So what is the essence of this is that, like if I have a like higher, like if I have a step size larger step size, if I use Richardson extrapolation, I will get a more accurate value to my differentiation of function compared to if I use central difference or forward. Okay, so this is the essence of that. Like we can use Richardson extrapolation, and so have you solved this problem in the assignment? Uh, there is a problem, right? Tan x. Did you solve that problem? F of x is equals to tan x. Anybody?
No, sir.
No. Okay. Uh, we'll just I'll just explain you uh, how to solve it using some other like like What are the other questions? So the first question is also cubic Hermitian polynomial, simply supported beam. The rotations are given. So the thing is like you should convert these degrees into radians and then solve the problem. So remember that like you have to convert the degrees into radians and like at the ends you know the displacement of the beam and also you know the slope of the beam. So you can obviously fit a cubic curve passing through these 2 points. So cubic Hermitian polynomial, like I hope you can solve that. And then after getting the polynomial, they are asking different things like downward deflection at midspan, location of maximum downward deflection, and maximum downward uh, deflection. So all these things are there. Like you can solve it. It's not uh, different, like a very difficult thing. Let's say I have like similar function. I will say like uh, f of x is some sin x. I will say f of x is sin x, and I want to find out uh, at f at x is equals to at x is equals to 1.5. Instead of tan x, I'm taking sin x here. Like you solve it for tan x, and you'll get the answer for the assignment. So at x is equals to 1.5, I want to find out what is the value of f dash of x using the Richardson extrapolation. So first, what I have to do, first step is like they have given three values of h. H1 is equals to 0.08, H2 is equals to 0.04, and H3 is equals to 0.02. Okay, these are the three values. So what I'll do is I will take H1, H2, H3, and I will use a central difference formula, that is f dash of x is equals to nearly equal to uh, f of x plus h minus f of x minus h divided by h. So you can just substitute uh, 1.5 plus h is 0.08 here. So I will write just h. You can substitute the value time 1.5 minus h divided by 2 into h. Okay. Similarly, for H2 and H3, you will get the values of f dash of x, and like this you can get. So you can see that uh, this is uh, this is similar to h by 2 and h by 2. Okay. So you can denote this as d1, d2, and d3. Whatever the thing which we are getting, you can denote this as like this. Or you can also like take this as phi of h and phi of h square. So here you can see in Richardson extrapolation. So this is the approximation, like using h and h square by 2, using h and h by 2, uh, I can get the value of derivative of the polynomial like this: phi of h by 2, 1 by 3, 1 by 3 phi into phi of h by 2 minus phi of h. So this is like something we can write it as like or I just write it. So the more accurate f dash of x, more accurate f dash of x will be 4 into uh, d2 minus d1 by 3. Okay. This is nothing but whatever which we get here. nothing, like you can write it as 4 pi of h by 2 minus pi of h by 2. So same as just simplifying this. Okay. So now you will get some approximation. You can write it as let's say E1. Okay. And similarly, using h h by 2 and h by 4, I can do another Richardson extrapolation, like using these two step sizes. I can get this as 4d3 minus d2 by 3, which is nothing but 4 into h by 4 minus pi of h by 2 by 3. So you will get some value. So d1, yeah, you will get some value. You will get some value of the function. So the thing is, uh, now using these two values and again using these two values, and I can extrapolate even further the approximate value of f dash of x by taking 16 into e2 minus e1 by 5. This will be like whatever the e2 and e1 values you get, you substitute here and you will get the answer. So this is the final answer. And these are like using the central difference, whatever the differentiation you get are the first three blanks. These are the first three blanks, and the final answer is this. Like first you have to do regression extrapolation of h and h by 2, then h2 and h by 4, and using those two values again. This is second level Richardson extrapolation, second level Richardson extrapolation. This is not given in the notes, but like I'm just directly giving you the formula. Like as we have seen, like here, the slope of this line in Richardson extrapolation of first order is slope is 4. If I take second level approximation, this will be even steeper and more accurate, and this will have a slope of 6. So that's what we are doing here, like using these two points. Like you just use this formula, like I won't write it and complicate it more, but this is the approximate. If you want the exact, like you can write it as 16 e2 minus e1 by 5 plus o of h power 6. So these are all the things which we are neglecting, and this can be taken as error. Okay, so this is the value. Did you do you did you get it, or you need some other like you need some more explanation?
Got it, sir.
Okay. Okay. Uh, yeah, but something you can do it. It's not a very complicated thing, but uh, do you want me to solve a similar problem for Gauss quadrature, or like, you will solve it on your own? Like anyone, if you
We'll try
want
it, sir.
me, you will try it. Okay. Okay. So the only thing, like is like, let's say, if you have some, I'll just tell you. Let's say you have some polynomial like this, or like some surface or manifold in 2D, you will have something like this. And let's like in 3D, it will look like something like some blanket, you can say. And you want to find what is the volume beneath this manifold or surface. So what we can do is like we can just take the integration, right? Take the integration on the domain. We will get the volume enclosed by this curve. But like we can do it numerically, like a lot of times, like if the curve is not smooth and like integration is not possible a lot of times, like as we have explained in the last class also. So at that time, like we have to resort to some kind of numerical integration. So one of the numerical integration techniques is Gauss quadrature. So Gauss quadrature, like we have also seen rectangular integration or trapezoid integration or Simpson's rule. Lot of numerical integration schemes are there, but the most efficient one is Gauss quadrature. So, but for Gauss quadrature, like let's say you have A to B, C to D, something like this. Your domain has something like this. Uh, in Gauss quadrature, we have to convert this into limits having -1 to +1. Okay, that is the most challenging, like, area or the most tricky part of this Gauss quadrature. So Z also, like you have to convert into eta and eta, and this is eta and eta. Okay, so you have to convert this in this form, and then we can write this as summation of weights into whatever this like this you can write. So if you are taking 2 points, then you will have four summations like uh, eta 1, eta 2 plus W2, eta 1, eta 2 plus W3 into Z of eta 2, eta 2 plus W4 into Z of eta 2, eta 1. Okay. And you are like given already, like if you are taking 2 points, these are the sampling points we should take for eta and eta. So if you are taking 2 points in 2D, like then you will get total four combinations, right? 1 by 3, 1 by root 3, minus 1 by root 3, and plus 1 by root 3, 1 by root 3, minus 1 by root 3, and both minus. So for all this, W weight is 1 only. So weight is 1, and you can do it and you can get, if you do the summation, you can get it. So this is the thing, like if you have any function like this, here, because let's say my 0 to 4 and y 0 to 2, and this is my function. into y. So now I have to convert these limits in the form of -1 to +1. So for that I can use this form. I can use this mapping x is equals to b minus a by 2 into eta. So x I'm mapping to eta. Okay. So 0 to 4, right? So 4 minus 0 by 2 into eta plus 4 plus 0 by 2. So this is my x. So 2 into eta plus 2. This is x. Okay. Similarly, y I can take as b minus, sorry, or you can say c to d, right? B minus c by 2 eta plus d plus c by 2. So that is 2 minus 0 by 2 eta plus 2 plus 0 by 2 is 1, like y is equal to eta plus 1. Okay. So now if I differentiate, like if I do this differential, you can get 2 into dx is equals to 2 into d eta. Similarly, if I apply differential here, I will get dy is equals to d eta. So here, uh, here dx and dy, we have to substitute this. Dx and dy, we have to substitute with these values. And x and y, we have to substitute with this one. Okay. So then you will get a function integration like this, which will have some form like this. So and you can do the evaluation. So so this mapping is the thing which we have to take care of. Other things are easier. So it's not difficult to do. Gauss quadrature. So uh, is it fine? Anybody? Yes, sir. Okay. Uh, uh, can you can you solve this fifth question in the assignment? Yeah, like were you able to solve the fifth question in the assignment, which is a cantilever being fixed at the left support and loaded at free end? What is the weighting function suitable to solve for vertical deflection? Anybody has an idea how which function is suitable here? Like they have given four functions, uh, which is suitable. Sachin, uh, Manoj, someone. Anybody is there?
No, sir, not sir.
So I will give a hint or like explanation. So whatever the weighting function which we take, like whatever the weighting function you take, it should satisfy the essential boundary condition. Essential boundary condition. Essential boundary conditions means like if you have a cantilever beam at this point, whatever the conditions with respect to the displacement or rotation of the beam are there, that should be satisfied. At cantilever beam at the fixed end, both the displacement and rotation should be zero, right? So this weighting function should satisfy that condition. So the weighting function, like if you put x is equals to 0, you should get w of 0 is equals to 0. And weighting function, like the differentiation of this at x is equals to 0 should also be equal to 0. That is the criteria it has to satisfy. So these are called essential boundary conditions. Essential boundary conditions should be satisfied at any cost. The weighting function should satisfy essential boundary conditions at any cost. If it is not satisfying, it is a bad weighting function. Okay. So in these in these four options, you can calculate w of 0 and also w dash of 0. So whichever function gives these values, that function will uh, be taken as a weighting function for your Galerkin method of weighted residuals. So today we don't have time. Like next week we will go deeper into these things. So we will look at more methods, and we will also dive into FEM. So so essential boundary conditions should be satisfied. At free end, we don't know what is the displacement and also what is the rotation. That is something which we have to solve using the Beam's equation, governing equation. So, but there is also a force at the free end that will be a natural boundary condition, not an exact boundary condition, not an essential boundary. So the weighting function should only satisfy this. It should satisfy the essential boundary conditions. Okay. Okay. Is it fine? Any doubts you want to ask me? You have any queries related to the course or assignment? Anyone? No?
No, sir.
Okay. So if you have anything, you can ask. Like you can always mail me. Like while you are solving it, it might be very dry right now, but difficult to understand a few things. But like trust me, like as we go on, like into the course, we will be able to understand more things, and that will make our life easier. So don't worry, like if you are not able to get a few things now, but you will understand as you go. Okay. Okay. If you don't have anything, we'll close. You don't have anything to ask, we'll close the class today. We'll meet again in the next Tuesday's session. Hope these sessions are helping you. I am trying to cover as much as possible. If you have any complaints regarding this session that you are not able to get it, or like you want me to cover something, you want me to tell or teach in some other manner, like you can openly say it to me here, or you can also write a mail to me that you want these things. I will be more than happy to adapt according to that and help you as much as I can. If you don't have anything, you can leave the class. You can leave the meeting. Thanks for joining. Hope you'll join the next session.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, guys. Have a good night.
Thank you, sir.